In this video, we're going to work one problem twice, basically. We're finding the area of a region bounded by these three curves, the x-axis, the square root function, and this line. And it turns out that there are two ways of doing this. There are two ways of doing most of our problems, but I want to show you that one is slightly more efficient than the other based on the geometry of the region. So the first thing we want to do with all of our area between two curves problems is graph the region. And you're graphing the region by graphing the individual curves. So we'll start with an xy plane. And of course the x-axis is down here, so we don't have much to do for the x-axis. And y equals the square root of x. We know what that looks like. Square root of 0 is 0. Square root of 1 is 1. Square root of 4 is 2, and so on, and it has that shape, that familiar shape of the square root graph. And then y equals x minus 2, that's just a line. When x is 0, y is negative 2, and the slope is 1, as the coefficient of that x is 1. So we're going to rise 1 and run to the right 1. So we're going to go up 1 and over 1, up 1 and over 1, up 1 and over 1, up 1 and over 1. Hey, there's a point on that curve. Looks like they intersect like this. And remember, the x-axis was also a bound. So this is our region. Now I can do this two ways. I can integrate with respect to x if I want to, by drawing all of my rectangles vertically. But notice what happens. For a little bit, for x between, it looks like 1 or 0 and 2, the top function is the square root and the bottom function is just the y-axis, or excuse me, the x-axis. So we've got the square root up here and the x-axis down here. But then as soon as we get to x equals 2, that changes. Now the bottom function isn't the x-axis anymore. Now the bottom function is this line. So I can do this. I can evaluate, or I can find this area by adding this area over here to this area over here. But there is an easier way. Here's our other option. Same region. I'm just going to be a little bit more, or a little bit less precise this time. I know they cross at 4 too. Look what would happen if I drew my rectangles horizontally. Do you notice that I always have the same function on the right? It's the line. And I always have the same function on the left. It's that square root. You might say, I'm not really sure I believe you. Well, just draw another rectangle and you'll see. The x on the right is from the line. The y, or the x on the left is from the square root. And it's true all the way down. It doesn't matter what y is, we get the same right function and the same left function. So this is going to be easier. This will allow us to find the area between the two curves with a single integral. But this time, because the width of that rectangle is delta y, we're going to be integrating with respect to y. Over here, I'd have to do two integrals. I'd be integrating from the bottom function to the top function for x between 0 and 2, and then for x between 2 and 4, I'd have a different top function and bottom function. So let's do it both ways and show that we get exactly the same answer. So we've graphed the region, and we've explored the two methods. Usually you would decide, I would look at these pictures and decide to integrate with respect to y, but we're going to do it both ways. Now that we've graphed our region, we want to find points of intersection. Actually, we can see from our picture that y equals x minus 2 crosses the x-axis, which is given by y equals 0. Crosses there when x equals 2, because if y equals 0, we get x minus 2 equals 0, which is 2. So I'm going to do that. So you set y equals 0 and y equals x minus 2 equal to each other and solve for x. So you have 0 equals x minus 2, which means x equals 2. So that's one point of intersection. And then here we've got the square root function and that linear function. If we want that point of intersection, you'll set y equals x minus 2. I didn't write equal to each other. Whoops. We're going to set y equals x minus 2 and y equals the square root of x equal to each other. And then you're going to solve for x. So we'll have square root of x equals x minus 2. Now this one is a little harder. We've been dealing primarily in this class with polynomial equations, or often with polynomial equations, whenever we're solving them. But we've got a square root this time. Remember what we did in pre-calculus or college algebra. We were trying to get rid of the square root so that it would look like something we're familiar with solving. To get rid of a square root, we use the inverse operation, which is the squaring function. So I'm going to square both sides, and I get x equals x minus 2 squared. That's not x squared minus 4, it's x minus 2 times x minus 2. So you FOIL, first times first is x squared, outer times outer is negative 2x, inner times inner is another negative 2x, so we get negative 4x, and last times last is 4. And now it's an equation that I know how to solve. Well, I knew how to solve that one too, but it looks more familiar. It's a polynomial equation. So we're going to subtract x from both sides, and we get this. I need two numbers that multiply to give me 4 that add to negative 5. I think x minus 1 and x minus 4 will work. So x equals 1 is one possibility, and x equals 4 is another possibility. Now, be careful here. Whenever you have a square root function, and you square both sides to get rid of the root, sometimes you end up with what are called extraneous solutions. These are the only possible solutions to this equation, but one of them might work and the other one might not. So we should check. Let's check x equals 1. When x equals 1, I've got the square root of 1 on this side equals 1 minus 2. Question is, are those equal? Is 1 equal to negative 1? No. So this one is not a solution, even though it looked like one. It's called an extraneous solution. And x equals 4, let's make sure that one works. Actually, I think we can tell that it works, but let's say we didn't know that. Got the square root of 4 on the left-hand side and 4 minus 2 on the right. Are those equal? Is 2 equal to 2? Yeah, so x equals 4 is the point of is the x value of the point of intersection, and if we want the y that goes with it, you just take the square root of 4 and you get 2. Okay, so we found the points of intersection. This wasn't necessary in this case, but sometimes you're doing the algebra, you look at the pictures and you really don't know where they cross. So to figure out where those lines or those curves are crossing each other, remember, set the y's equal to each other and solve for the corresponding x value. Okay, so now I want to integrate this, or I want to set up the integral for this, or the sum of two integrals for this. And I want the area to be in terms of x. So we're going to have two integrals, one for x between 0 and 2, and another for x between 2 and 4. For each of these, we need a top function and a bottom function. For this first interval, for x between 0 and 2, the top function is just y equals the square root of x, and the bottom function is just y equals 0. So we're just taking this y and we're subtracting that y, and we get square root of x minus 0, so just square root of x. Over here, the top is still square root of x, but the bottom is given by x minus 2 this time. Don't forget your parentheses, you've got to distribute that negative to both of them. So this is our area, and I want to evaluate it down here. We're going to come back to this picture so we can see that we get the same result if we integrate with respect to y. So we're going to have the integral from 0 to 2 of the square root of x, which is x to the 1/2, plus the integral from 2 to 4 of square root of x, which is x to the 1/2. If I distribute that negative, I'm going to have a minus x, and a negative 2 is a positive 2. Now we're going to use the power rule. Add 1 to the exponent, that's 3/2, divide by the new exponent. Dividing by 3/2 is multiplying by 2/3. Plug in 0 and 2 and subtract. Over here, add 1 to the exponent. 1 plus 1/2 is 3/2. Divide by the new exponent. Dividing by 3/2 is multiplying by 2/3. Bring the negative down. There's an implied 1 there. Add 1 to the exponent. Divide by the new exponent. The antiderivative of a constant is the constant times your variable, which in this case is x. We're going to evaluate that from 2 to 4. Okay, so we've got 2/3 times 2 to the 3/2 minus 0. And then if we substitute in 4 over here, we've got 2/3 times 4 to the 3/2 minus 1/2 of 4 squared plus 2 times 4. And then when we substitute in 2, we're going to have minus 2/3, 2 to the 3/2 minus 1/2 of 2 squared plus 2 times 2. Okay, so this is our answer, it's just not simplified. Now, well, actually, I'm just going to leave this one alone. We don't really need to write the minus 0. This one can be simplified, but we'll simplify it later. I've got 4 squared is 16, half of 16 is 8. And we're adding 8 there, so the 8's reduce and those are gone. And I have minus 2/3 of 2 to the 3/2. Hey, that cancels with that one. And I have minus a minus, that's going to be a plus. Half of 4 is 2. And we're subtracting 4 as well. Okay, so this is our answer. It's this plus 2 minus 4, and that simplifies a little bit. Two minus 4 is negative 2. Okay, so that's our answer. But this can be simplified. It's probably been a while since your algebra classes, but if you've got x to the m over n, so x to a power, and that power is a fraction or a rational number, you can take the nth root of x and raise that to the m, and it's the same thing. You can also take x to the m and then take the nth root, and that's the same thing. But when I'm dealing with numbers like this 4 to the 3/2, I want to do this one because taking the nth root of something is going to make it smaller. And then I'll have a smaller number that I raise to a power, rather than taking a larger number and taking the nth root of it, which I might not know as easily, as intuitively as I know this one. So with that in mind, this is 2/3, and that 2 in the denominator tells me I'm taking the square root of 4, and then I'm cubing it. And we're going to subtract 2 from that. Square root of 4 is 2. 2 cubed is 8. 8 times 2/3 is 16 over 3. And we're subtracting 2, which is 6 over 3. So we get 10 over 3. A lot of work for 10 over 3, and a lot of arithmetic. You can also use your calculator for this arithmetic at the end if you want to. So we graphed the region, we found points of intersection. Then we identified A and B, We identified top functions and bottom functions. We plugged them in. And then we did a little bit of algebra to simplify, and then we evaluated the integrals. It's actually very, very simple. Now this is very similar, but you have to be careful. This is given by the equation y equals x minus 2, and this curve is given by the equation y equals square root of x. But whenever I am finding the height of this, or the length of this rectangle, it's x on the left minus x on the right, and they're both x's as functions of y because of the delta y. So you gotta be very careful. I can't just take this function and this function. I need to get x by itself first so that x is a function of y. So let me show you what I mean. The area is going to be the integral from c to d of the top function of y minus the bottom function of y, dy. And our y values looks like they go to, this was x equals 4 and that was y equals 2. So c and d are 0 and 2 because we start at the bottom and we go to the top. We're integrating with respect to y, so I need bounds that are involving y. Okay, careful here. The top function is, or the right function, x on the right is the line. So this is x right minus x left. But you need x on the right as a function of y. So we need to take this and solve for x. Add 2 to both sides and you get x equals y plus 2. So that's x on the right. And then over here, this is similar. We want x on the left. Y is the square root of x on this curve, but I don't want square root of x. I want x as a function of y. So we square both sides, and we get x equals y squared. That's easy. So that's what we're going to integrate, and hopefully we get 10 over 3. All right, so we're doing this one this time, and we're hoping to get the same answer. So I've got the integral from 0 to 2 of y plus 2 minus y squared. There's an implied 1 there. So you want to add 1 to the exponent, divide by the new exponent. The antiderivative of a constant is your constant times your variable. Here, bring the negative down. Add 1 to the exponent, divide by the new exponent. Plug in 0 and 2 and subtract. So we're going to have 1/2 times 2 squared plus 2 times 2 minus 1/3 of 2 cubed. And then if y is 0, this is 0 plus 0 minus 0, so we just get 0. It's half of 4. Half of 4 is 2. That's 4. And I've got minus 8 over 3. So 6 minus 8 over 3. 6 is 18 over 3. 18 over 3 minus 8 over 3 is 10 over 3. Hey, we get the same thing, but we got the other way. So you can see this was much faster and easier, but you did have to be careful. You need x as a function of y on the right. So x on the right was given by this equation, but I needed to get x by itself first. And I need x as a function of y on the left as well, also given by y equals square root of x, but I need to get x by itself first, so I can find out what x is in terms of y and substitute that in. And that's it for that one.